So let's take a look at the definite integral. So the main thing to keep in mind here is that derivatives and integrals are opposites, and that while derivatives represent the slope of the curve, the integral will represent the area under the curve. So let's look at the notation of an integral. So right here we have the integral from a to b of some function, let's call it f of x, and then times dx. Now the main parts of this integral, obviously we have the function itself, f of x, we have the integral notation, which looks like that, and then we have our bounds. So our lower bound is a, and our upper bound is b. And we read from a to b, so from bottom to the top. Now the dx here represents the variable we're going to integrate with respect to. So because we have dx, we're going to integrate with respect to x. If you have dy, you're going to integrate with respect to y. Now keep in mind, if you have dx and x is the variable of integration, your function must be in terms of x, and your bounds must be in terms of x as well. However, if you're going to integrate with respect to y, so you have dy, then your bounds must be in terms of y. So let's just put c and d. So those represent the y bounds, and then our function must be in terms of y as well. So once again, this is read as the integral from a to b of f of x dx. Now in order to understand what this means, let's go ahead and actually graph this. So if I were to just graph the standard xy plane here, let's go ahead and say this curve is f of x. And then the bottom bound a is right over here, and the top bound b is right over here. Once again, we are integrating with respect to x, so these are going to be the x bounds. Now once again, the integral represents the area under the curve. So basically all we're looking for when it says the integral from a to b of f of x dx, we're just looking at the area under f of x from the x bounds of a to b. And that's basically it. Now notice the title of this video was the definite integral. Now there are two main types of integrals. There's a definite and an indefinite. Now the only difference is in a definite integral, which we'll be talking about in this video, it has bounds. So let's go ahead and call it from a to b. So we have the integral from a to b of f of x dx. And in an indefinite integral, it just doesn't have bounds. So we just leave it as it is. And we will talk about indefinite integrals in a future video. Now let's look at some properties of integrals. Similar to how in derivatives we had different rules, similar things apply here with integrals. So first, let's say we have the integral of f of x dx. And this time the bounds are not from a to b, but the bounds are from b to a. Now let's say you want to just flip the bounds and say the integral from a to b of f of x dx. Well, all you have to do when you flip-flop the bounds is to multiply by -1 or make the integral negative. Now the second property here, let's say you have the integral of f of x dx and the bounds are the same. So in other words, the upper bound is a, the lower bound is a as well. If that's the case, then the answer is just going to be 0 when you evaluate the integral. Now the next property here, let's say you have the integral from a to b of some constant times dx. Well, the answer to evaluate, or the way to evaluate this integral, all you have to do is take the constant times b minus a, or in other words, the constant times the upper bound minus the lower bound. And I'll show you a visual representation of why that is. So let's say we have, instead of the constant, let's just pick a random value like 3. So we have the integral from a to b of 3 times dx. Now if you go ahead and actually graph y equals 3, once again that's just going to be a straight horizontal line. 1, 2, 3. So that's going to be y equals 3. Now let's go ahead and just say our bounds, our lower bound here, a, is right here, and our upper bound b is right here. Once again, the integral is the area under the curve. So if we were to find the area under the curve, all we're looking for is this, which is the area of a rectangle. So in order to find the area of a rectangle, obviously we need base times height. Well, the height is just the function itself, y equals 3. That's going to be 3. And now in order to find the base, we just need to find the distance between our two bounds, a and b. And in order to find that, all we have to do is take the difference between the two. So b minus a, or in other words, the upper bound minus the lower bound. So in order to find the area of the rectangle, once again, base times height. So 3 times b minus a, or in other words, that matches our formula of the constant times b minus a. So that's how you evaluate the integral of a constant. Now for the next property, let's say you have the integral from a to b of one function f of x plus or minus another function g of x times dx. This is very similar to the sum and difference rule for derivatives, where if you do have a plus or minus here splitting two different functions, you can take the integral of each individual function. So we can split it up into the integral from a to b of f of x dx plus or minus another integral from a to b of g of x dx, the other function. And so now the final property, let's say you have the integral from a to b of a constant times a function f of x dx. Well, similar to how in derivatives where you can take the constant outside the derivative, you can also take the constant outside the integral and just evaluate the integral of the function. So you can rewrite it as a constant times the integral from a to b of just f of x dx. Now let's say you're trying to find the total area under the curve f of x and the bounds range from a to c. So in integral notation I can write it as the integral from a to c of f of x dx. Now the good thing with this is you can also split it up into two different sections. So let's say the first section ranges from the x values of a to b, and the second section ranges from the x values of b to c. So you can break this integral up from a to c into two different integrals. So we have the integral of this first section from a to b of f of x dx, and then plus the integral from b to c, that second section, of also f of x dx. Now for this first problem here, the graph of g, which is shown below, consists of two straight lines in a semicircle. Use it to evaluate each integral. So for part A here, we have the integral from 0 to 2 of g of x dx. Once again, g of x is this curve outlined in blue. And we're trying to find, for this first part here, the integral from 0 to 2. So those are our x bounds. Once again, integral is the area under the curve. So for x bounds range from 0 to 2, we're basically looking for this area here. Now the good thing here is we can just use the formula to find the area of a triangle. So once again, the area is going to equal 1/2 base times height. So in this case, it's going to equal 1/2 times the base. Once again, it goes from 0 to 2, so the base is 2, times the height, and the height is going to be 4. 2 times 4 is 8, 8 times 1/2 is 4. So we get the area equals 4. So I'm going to put that right underneath this area here. Now for part B, we need to find the integral from 2 to 6 of g of x dx. So our x bounds range from 2 to 6. So we're basically looking for the area under the semicircle here. Now we can just go ahead and use the formula to find the area of a semicircle. So area is going to equal pi r squared divided by 2. So the radius here, now this isn't necessarily drawn to scale, and I apologize for my drawing, but the radius here is supposed to be 2. So we can go ahead and say the area is going to be equal, I'll go ahead and erase that radius here, okay. Area equals pi times 2 squared, which is 4, over 2. 2 over 4, or 4 over 2 is 2. So the area equals 2 pi. Now be careful here because the area under this curve here is below the x-axis. And just a thing to keep in mind, whenever the area is below the x-axis, it's going to be a negative area. So for example, in part A where we had this area which was above the x-axis, that was a positive area. But this area is below the x-axis, so it's a negative area. So it's not positive 2 pi, it's negative 2 pi. Now for part C, we have the integral from 0 to 7 of g of x dx. So we're going from the x values of 0 all the way to 7. And so we basically have to look for this area, and also this area. Now the good thing is we've already found two of the sections here. We've already found the one from 0 to 2 and the one from 2 to 6. So we can break this integral up into three different integrals and say the integral for the first section from 0 to 2 of g of x dx plus the integral of the second section from 2 to 6 of g of x dx, and then plus the integral of the third section, this one's from 6 to 7, the integral from 6 to 7 of g of x dx. And the good thing is, once again, we've already found two of these, we just need to find this last one here. So in order to find the integral from 6 to 7 of g of x dx, all we have to do is find the area of this triangle. So once again, area is going to equal 1/2 times the base. Now the base goes from 6 to 7, that's going to be 1 times the height, and the height, be careful here, is just going to be 1. So we have 1/2 times 1 times 1, and that's going to give us an area of 1/2. Because this area is above the x-axis, it's going to be positive, so positive 1/2 is the area. So now we can just go ahead and find the integral from 0 to 7 of g of x dx by adding up all those smaller sections. So we have the integral from 0 to 2 of g of x, which was 4, plus the integral from 2 to 6, which was a negative 2 pi, and plus the integral from 6 to 7, which we've just found to be 1/2. So now we have 4 plus 1/2, which is going to be 8 over 2, plus 1 over 2, which is 9 over 2. So the final answer is 9 over 2 minus 2 pi, as the total area under the curve of g of x from 0 to 7. Now for this next set of problems, let's go ahead and evaluate the integral by interpreting it in terms of their areas. So for number 1, we have the integral from 0 to 3 of 1/2 x minus 1 dx. Once again, the integral is the area under the curve. So in order to find the integral, let's go ahead and actually graph this function, 1/2 x minus 1. So if we were to go ahead and graph this, our y-intercept obviously is negative 1. And then we have 1/2 as a slope, so up 1 over 2. And then let's go down 1 to the left 2. So the line looks something like this. Now we want to find the integral from 0 to 3. So our bounds range from 0 all the way to 3. So this is basically the area that we're looking for under the curve. Now we can go ahead and actually, to make it easier to evaluate, split this integral into the integral from the first section, which goes from 0 to 2. So from 0 to 2 of 1/2 x minus 1 dx, and then plus the integral of the second section here. This is from 2 to 3 of 1/2 x minus 1 dx. And the good thing here is both of the areas represent the area of triangles, so we can just use the formula to find the area of a triangle. Now let's go ahead and start with the integral from 0 to 2, so this section here. Now once again we're just going to use the area formula here for a triangle. It's going to equal 1/2 times the base here is 2, and then times the height, which is just going to be 1. 2 times 1 is 2, 2 times 1/2 is 1, so we get the area. Now once again this area is below the x-axis, so the area is -1. So I'll put -1 underneath that integral. And then we have plus the integral from 2 to 3. I'll go ahead and erase this bottom section here. Just looking at this section. So once again the area equals 1/2 times the base. The base is just going to go from 2 to 3, so that's going to be 1. And then times the height. Now we don't know what the height is, but once again this is at the x value of 3. So I can plug in 3 into the function and find what the height is or what that corresponding y value is. So I go ahead and plug in 3 for x into the function. We get 1/2 times 3 minus 1. 3 times 1/2 is 3/2. Minus 1, or minus 2 over 2. 3/2 minus 2 over 2 is going to be 1 over 2. So the height is going to be 1/2. So multiply by 1/2 here. 1/2 times 1/2 is 1/4. 1/4 times 1 is still 1/4. So we get the area equals 1/4. This area is obviously above the x-axis, so it remains positive 1/4. So now we have -1 plus 1/4, or in other words, -4 over 4 plus 1 over 4, which is going to give us -3 over 4. So that's going to be the area, or in other words, the integral from 0 to 3 of 1/2 x minus 1 dx. Now for number 2, we have the integral from -3 to 0 of 1 plus the square root of 9 minus x squared dx. Now the very first thing I would do here is, because there is a plus here, I can split this into 2 different integrals. So the integral from -3 to 0 of 1 dx, and then plus the integral of from -3 to 0 of the other term, so the square root of 9 minus x squared times dx. Now for this first integral, realize that all we have is the integral of a constant. So we can just use the formula where we take the constant times b minus a, or in other words, the constant times the top bound minus the lower bound. So in order to evaluate this integral, we can just take 1, which is the constant, times the top bound, which is 0, minus the lower bound, so minus -3 means plus 3. 0 plus 3 is 3, 3 times 1 is 3. So we can go ahead and put that the integral from -3 to 0 of 1 dx is just going to be 3. And now for the second integral, we have the integral from -3 to 0 of the square root of 9 minus x squared dx. So we need to actually go ahead and graph this. Now, the square root of, or the formula where we have the square root of some constant a squared minus x squared, that's just going to be the formula for a semicircle, where a is going to be the radius. Now we can go ahead and actually rewrite the square root of 9 minus x squared using this formula here as the square root of 3 squared minus x squared. So in this case, our radius, or a value, is equal to 3. So all we're doing is we're basically drawing a semicircle that's above the x-axis with a radius of 3. Now if this semicircle has a radius 3, we can tell that this left x bound here is -3. We obviously have positive 3 here, and the upper y bound is also positive 3. Now if I go ahead and erase that radius, notice our integral is the integral from -3 to 0 of the square root of 9 minus x squared. So we're basically trying to find the area under this function going from the bounds of -3 to 0. So -3 is obviously, we just labeled it right here, and then 0 is in the center. So we're basically looking for this area here. Now this is basically a quarter circle, the area that we're looking for. So we can use the area formula where it equals pi r squared over 4 this time. So the area equals pi times, now the radius is 3, remember, so 3 squared is 9 over 4. So we get the area equals 9 pi over 4. So the integral from -3 to 0 of the square root of 9 minus x squared is going to be positive 9 pi over 4. So then when we add those together, 3 can be rewritten as 12 over 4. So then for our final answer, we get 9 pi plus 12 all over 4.